Hello everyone. This is Team Machine Minds, and our project is cross-cultural humor and sarcasm detection, or in simple words, memes. We have a paper, Momenta, and we'll be discussing through that in this presentation. The motivation behind doing this. Like I said, memes are one of the most popular forms of communication in today's world, for jokes or for, expressing hatred or whatever. And that's exactly the issue with it. Memes are sometimes used to express hatred, to be offensive to certain groups, and to be harmful to communities. And that's what makes it important to detect them if they are harmful to any group or any target. So, what makes this task appreciable? Now, it's because memes are a multimodal form of communication. So, they involve text, sometimes audio, but it's mostly text and just images. So, a few examples are ones which you can see right below. So, it's not just one singular thing that you have to analyze. You have to analyze how the image and the text interacts, and that's what makes this challenging. What we basically do is, one sec. Yeah, next slide. Yeah, so the previous work that was done in this is some of the models like late fusion or concat-BERT. For example, what late fusion does is it takes the text and it encodes it, and then it takes the image and it encodes that into two vectors, and it trains the model on both of those vectors and combines the outputs of the two. And what concat-BERT does is it gets both the embedded vectors from the text and image and concatenates them into one singular vector and then trains the model on that. And there are some other models such as Wilbert and Wilbert Co. But some of the problems with the existing work that has already been done here is they have been trained on offensive or hateful content. So, when it is specifically directed towards a certain group or a certain community, say a minority community. But not all memes are like that. Suppose take memes on engineering, for instance. Now, it's not hateful or anything to any group, but they are harmful in general to the community. It can set perceptions, it can give opinions to people that are actually false. And detection becomes hard there, and work has been done less in that side of the area. So that's one problem with the previous work that's been done. And now we will proceed with our presentation.
Now coming to the general terms that were used in this paper, firstly defining what harmful memes are. Harmful memes are those which include abusive or offending content which mostly ridicule or mock a person or an idea. Coming to what the model in this paper identifies. So the model in this paper identifies basically two groups. About one target is about harmness and the other target is about which target group is being affected. Coming to the target categories, the paper divides it as we divide it as individual, meaning it's a person, usually a celebrity. It could be an organization, say a political party. It could be a community, community based on religion, culture, or gender, or the society as a whole, say all people working from home also. Coming to what degree of harmness the paper decides. So there are three levels of harmness. Very harmful meme. So it is basically like the image and text don't are harmless individually, but when fused together, they have a very harmful meaning. Partially harmful meme meaning they have some degree of harmness, but it's often subtle mockery and not very offensive content. A harmless meme is one which has no hidden layers of offensiveness. Coming to the architecture of the model used in this paper. So, firstly, we have a meme over here in the left side. So, firstly, from this meme, many proposals are made. So, these proposals include regions such as the face of the person, the extracting features like what his expressions are, and text content within the image. So, all these regions are cropped and resized, and they are plugged into a VGG19 model. This is a CNN model which is used to extract features from these images. So, say there are n proposals, then we would have n vectors. So each vector is of 4096 dimension, and all those are or say concatenated, and it's a weighted average actually. So when we do a average, we get a single 4096 dimensional vector. This is the first path. Coming to the second path, this image is directly plugged into an image encoder, and this clip image encoder is trained on 400 million uh, input and output training data. So it's basically an image and the caption of that image. So this image encoder returns a 512 dimension vector. So this path is basically identifying the global features present in the image, and this path is identifying the local features present in the image. Coming to the text part of the image, so we use Google socio. It's for identifying all the text content within the image, and all this text is then encoded into a 512 dimension vector using the clip text encoder. Then there are these attributes which are extracted from the proposal regions and from the meme. So these attributes are similar to adding background knowledge about the image. So this meme is most related to election 20. So this is some attribute which won't be captured in above parts, but it is something which is relevant to this meme. So we find all those attributes, we encode it using distillbert. So say there are m attributes, then we would have m cross 768 dimensional matrix, and we again have a weighted average over these all these vectors, and we get a 768 dimensional vector. We can have see the formulas of the weighted average over here, h hat and g hat. Now, what this intra-modality attention does is it's basically like fusing the global features and the local features of the particular modality, say entirely text or entirely image. So here the local and global features of image are added together. So firstly, this 4096 dimensional vector is reduced to a 512 dimension vector. After that, it is concatenated with the F1 vector, this one, Fi vector, and then it's multiplied with a weight matrix to get a final 5 dimension vector. Here also in a similar manner, this 768 dimensional vector is converted to a 512 dimension vector. It is then concatenated with the Ft and then multiplied with a matrix to get the 512 dimension vector. Now CMAF is cross-modality attention fusion, wherein the text and image embeddings are concatenated together. And on concatenating, we don't directly concatenate. We find an attention value, which is AV and AT. AV is basically the attention, it is basically a representative of harm the image carries, and AT is a representative of how much harm the text carries within it. This one is added for removing the problem of vanishing gradient descent. And with this attention values, these two are firstly multiplied. So it's scaling. And after that, these are concatenated and multiplied with a weight matrix to get a final 512 dimension vector again. And from there are two downstream tasks, finding the harmfulness of the image and the target of the image. Coming to what's the loss function used over here. So firstly, if the image is harmful or partially harmful, then we check if the target is rightly identified or not. If the image is not harmful, then we don't care about the target. It's a cross entropy loss, but dependent on the harmfulness of the image. Coming to the contributions made by this paper. So firstly, they have introduced two large scale data sets, HarmC and HarmP. HarmC is regarding memes about COVID-19, and HarmP is regarding the US politics in 2020. The second major contribution of this paper is the MOMENTA model. It's a deep neural network model that combines local and global features of the meme, and also it makes the meme context aware by adding attributes. Coming to results it has outperformed 10 baseline models, and also it has better transferability and interpretability as well. Next, we move on to the future.
Now that we have seen the contributions of momentum, before we go into our actual experimental plan, let me just briefly share the future directions and novelty extensions that this work can take. In short term, there are some paths we can take forward. First, the harmful meme detection needs to expand across languages, regions, and cultures. Most datasets today focus only on English or Western content. By adding multilingual and multicultural data, we can make the system more fair and useful worldwide. Second, we should broaden the scope to multi-domain datasets. Memes look very different in politics, social issues, entertainment, and other areas. Handling this diversity will make the models more general and reliable. Third, we can connect the system with external knowledge bases, such as political or social context. This will help the model not just read the text and image, but also understand the intent and background behind it. Another step is to move beyond simple harmful versus non-harmful labels. Instead, we can classify the more detailed type of harms like misinformation, socioeconomic harm, or psychological harm, giving us a richer understanding of the risks. And since many memes are also include voice or music, another direction is to extend the system to support audio inputs as well. That would make the detection more complete for modern meme formats. Looking further ahead, there are also some long-term visions. One is explainable models, where the system clearly shows which part of the meme, whether text, face, or background, causes the harmful labels. This builds trust and makes moderation exciting. Another exciting transparent thing can be instead of stopping at the detection, the system could actually suggest safe or positive alternatives, almost like turning harmful content into constructive content. Next, we can move on to our actual experimental plan.
Audio on zero. Audio on.
Next slide. So I'll be discussing the experimental plan of our project. The first step is the dataset curation. In this, we plan to spend the first 25 days collecting memes from several online platforms and as well as public meme repositories in four Indic languages, Hindi, Telugu, Tamil, and Kannada. We'll curate a balanced dataset of at least 8,000 memes in each language and then annotate them with both the intensity of harm as well as the intended target. This step will result in curated dataset as well along with the pre-processing code. So the next step is baseline experiments and fine tuning. In this, we plan to spend the next 10 days. So we'll train baseline models including IndicBERT and ResNet, Clip, VisualBERT, Wilt, Momenta, NoMeme, and Mind. Also zero shot evaluations. We will record performance metrics such as accuracy, precision, recall, F1 score, and MMAE before and after fine tuning. The outcome of this stage will be a baseline performance report and model checkpoints. The third step is comparative and cultural context analysis. We plan to spend 1 week on this part, and in this, we'll use interpretability tools like attention maps and LIME to visualize the modal focus, and then we'll conduct human evaluation to analyze cultural appropriateness and potential biases in outputs, especially for satire, stereotypes, and political differences. The deliverables for this step will be interpretability and bias analysis. The next step is context, common sense integration, and pipeline exploration. We plan to spend 4 weeks on this, and why we are doing this step is since many harmful memes only make sense if you know the background story of it. We plan to integrate common sense knowledge bases such as ConceptNet and Atomic into our multimodal pipeline. We'll also conduct ablation studies to test the contributions of different modalities and knowledge components, and also extend interpretability analysis on these enriched models. Evaluation will again rely on the same metrics as above. They are accuracy, precision, recall, FN score, and MMAE. This stage will produce the model pipelines, ablation study, and final performance results. Thank you.